So today we are doing 2.2, which is Algebra of Functions, which is really what it sounds like. We're going to learn how to do the 4 basic operations with equations or with expressions. So you can add, subtract, multiply, and divide numbers. So you can do the exact same thing with equations and with functions. That's what it comes down to. So when you look at these, like the sum, it says f plus g of x. That's exactly the same thing as saying you're taking the function of f and you're adding to it the function of g. Subtraction, you're taking the function of f minus the function of g, multiplying them together, and then dividing them. It's the same thing. The only stipulation whenever you do division is that the function of g cannot equal 0 because we can't divide by 0. That is the one stipulation that we have. So let's see how this plays out with one of our problems. It says, given the function f of x equals x plus 1 and g of x equals the square root of x plus 3, we're going to find f plus g of x. Well, f plus g of x is the same thing as taking f of x. I'm not going to write that. Plus g of x. I can just slide it over. When you take f of x plus g of x, you're taking x plus 1, and you're adding to that the square root of x plus 3. Do not make this complicated. You can't combine those. They're not like terms. You can't do any special magic math to make it work. That's literally all you do. Now, sometimes you will be able to combine like terms. I'm not saying that'll never happen. But in this specific situation, because we have a variable and a constant and then a radical, we can't actually join those together any further. So we leave them be. So that's all you have to do. Now, for B, we get to actually do something. For B, we have f plus g of 6. So notice this time it doesn't say f plus g of x. This time we're going to plug in a number. The nice thing is we already know what f plus g of x is. It's this x plus 1 plus the square root of x plus 3. But now, instead of having it in terms of x's, we want it with 6. So we're going to plug a 6 in anywhere that there's an x. So that instead of x plus 1, we now have 6 plus 1 plus the square root. Instead of x plus 3, we have 6 plus 3. We substituted in the 6. That's all we did. Now we can simplify, and we're going to do that. Because we have 7 plus the square root of 9. What is the square root of 9? 3. Meaning we get 10. So sometimes you will have it where the function is still going to be in terms of x, like in our first example, and other times it's going to be like B, where it's in terms of a specific number. If it's in terms of a specific number, then wherever there's an x in your functions, you put in that number. Questions on those first two? Pretty straightforward, yeah? Hopefully. Okay, what if it says f plus g of negative 4? What do you guys think? We're going to do exactly what we did, where we put the negative 4 in place of the x. Do we see a problem?
It's going to make the number under the square root negative.
Yeah, we got a problem. When we have a negative under a radical, we get a not real number. We get an imaginary number. And when we get an imaginary number, that means there's no solution. We have to get out a real number in terms of what real numbers are from back in Math 20. There's complex numbers that encase real numbers, but then inside the complex, there's real and imaginary. And if you take the square root of -1, you get an imaginary number. So if this happens, then you need to stop, and there's going to be an option where you either type in your answer or the option is that there's no solution, and you'll select the no solution. Questions, comments, concerns? Okay. Let's find the domain of these algebras of functions. These look scary. They're not too bad. Remember, the domain is what x's you can plug in to your function. And in general, the domain for a function is always what? Does anybody remember? Yeah, it's always everything. And there was 2 special cases. So maybe it's good to write this down again. The domain for a function is always -infinity to +infinity, unless you get one of these 2 cases. One, there's an x under an even-rooted radical. 99% of the time, that even-rooted radical will just be a square root. But we say even-rooted because if it was a 4th root or a 6th root, this is still one of those exemptions. Oh, thank you. Tell me to slide it up. Still trying to leave that other stuff in there. So either x is under an even-rooted radical, or x is in the denominator. Or as we saw previously, you could have some combination or both of those things happening at the same time. But whenever we have those situations happening, then we have what I always have dubbed trouble spots. Because if x is underneath an even-rooted radical, as we just saw above in the previous problem, we don't want negative numbers. We can have 0, that's totally fine, but we don't want to have negatives under our radical. And so we have to eliminate those x's that give us a negative under the radical. And if x is in the denominator, we don't want it to go to 0, because then that causes a problem. So then we have to eliminate the x values that cause our denominator to go to 0. And so as much as the sum and difference, product and quotients domains up here of these algebras of functions, as much as it says this stuff, I'm going to tell you 90% of your sum, difference, and products are going to be -infinity to +infinity. Because the only issue you could have in there are one of these 2 situations. And so while finding the domain of the sum is where you take the domain of f and you intersect it with the domain of g, that is true for all of these, which is great. Really what you're going to do is you're just going to look at the end product, the end solution that you have once you've taken your algebra of functions, and you're going to say, okay, well, is there an x under the even-rooted radical, or is there an x in the denominator? If your answer is no to both of those, then you have -infinity to +infinity as your domain. If you do have one of these exemptions, then you'll go through the process like we've done previously, where we eliminate out those trouble spots. So this is good information to have where we talk about the intersections of our domains. But when we go to apply it, I think it gets a little bit easier than what this makes it look like. So now we're going to deal with 2 new functions. We have f of x equals x minus 4, and we have g of x equals x plus 2. And they are asking us to find f plus g of x, and then also find its domain. So even before we find what the algebra of the function is, look at those 2 functions. Do we have a radical? No. Do we have a fraction where x is in the denominator? No, we don't. So our domains are going to be really easy. Really, really easy. Because if we don't have one of those two situations going on, then when we add, subtract, or multiply them, it doesn't change anything. Our solution is still going to have a domain of negative infinity to positive infinity. The only one that's going to change then is when we do our division, and that's simply because we're going to put g of x in the denominator, which then is going to cause us a trouble spot or two. So if we are adding these two functions together, we take x squared minus 4 plus x plus 2, because that was our f of x function, the x squared minus 4, and we're adding to that our g of x function. And this is one of those times when we can go further. We can simplify another step because we have a minus 4 and a plus 2, so we can combine those together. Now, do not be tempted to solve this. It's not set equal to 0. We aren't told to find solutions. We are just told to do the algebra functions. So that is all we're going to do with it. We combined it all together. We have it written in descending order. We have no further like terms to join together, so we are good to go. Then we can look at the domain. I guess there's something else on that page. I do show it using the intersection just so you can see what's going on. But really, what you can do is just look at the end solution that we had, which is x squared plus x minus 2. And you ask those two questions. Is there a radical? No. Is there a fraction with x in the denominator? No. So the domain of that function, that newly found algebra function, is still negative infinity to positive infinity. Are we good if I flip it? I wrote given the f of x part again at the top of this, but that's just because I had to flip my paper over. It's the same functions. We're going to do the subtraction, the multiplication, and the division for those two functions, for that f of x equals x squared minus 4 and the g of x equals x squared, or excuse me, x plus 2. We're going to do that, and we're going to find the domain on each of those steps. The one thing you do want to be careful about is when you take the subtraction of the functions, notice that I put g of x inside of parentheses because I am subtracting all of g of x. So I have to distribute that negative inside the set of parentheses. I can't just put minus x plus 2 because then I will get the wrong answer. So that is something to be aware of as you do your algebra of functions, that minus that goes in between your two functions applies to everything that is in g of x. So I'm going to distribute the negative to the x and to the 2, and then I'm going to combine like terms. So I have x squared minus x, and then I had a minus 4 and a minus 2, which gives me the minus 6. Very similar to the last example with the addition of those two functions. I don't have a radical. I don't have a fraction. So the domain of f minus g is going to be negative infinity to positive infinity. Slide on down and we can look at the product of these two functions. That's where we multiply them together. And this is where hopefully you can dust off a little bit and think about FOIL, because we have a binomial in f of x, which is x squared minus 4, times another binomial in g of x, which is x plus 2. And when we take a binomial times a binomial, we have to FOIL. Down here, I'll show you the slightly longer. When you do FOIL, you do your first, will give you x to the third. You do your outer, which will give you 2x squared. Your inner, which is a minus 4x. And your last, which is negative 4 times 2, which is negative 8. If you draw the little connectors like I do, I always think it kind of looks like a face where these are eyebrows and that's a nose and a mouth. And then that's how you know you've FOILed. There's nothing left to combine, so you're done with that. And then coming up with the domain, again, is the exact same process as the previous two examples. There is no radical, there is no fraction, so you have negative infinity to positive infinity. When we divide our functions is where we're finally going to see, in most of our cases, where we're going to see our first instance of a trouble spot. Because even if both of the original functions are nice and linear or quadratic or they don't have any trouble spots in and of themselves, as soon as we divide them, we can have trouble spots. So if I'm taking f divided by g of x, then I'm putting the function f of x over the function of g of x. Now, hopefully that x squared minus 4 sparks a little reminder in your mind that those are a difference of squares. Difference of squares means that you factor, if you have, here's the general, if you have a squared minus b squared, a difference of squares means you have an a minus b times an a plus b when you factor it. X squared is obviously a squared, and then 4 can be a squared because it can be 2 squared. That means this factors into x plus 2 and an x minus 2. Why is that important? Well, because if we have an x plus 2 times an x minus 2 on top and an x plus 2 on bottom, we actually have stuff that's going to cancel. Leaving us with just an x minus 2. Now, you may say, okay, well, if I look at just the x minus 2 bit, then I don't have any problems. And that's correct, you wouldn't be. But we have to consider the fact that we had a fraction, and for a while, we had an x plus 2 on bottom, which means there would be a trouble spot that we have to eliminate out. That's why we look at it in the bigger picture with the unions and the intersections. Because even if I eliminate it here, if I plug it in, oops, sorry, I'm up here. Where'd I go? Right here. If I plugged in x is negative 2 anywhere up here, I'm still getting that problem where I'm going to have 4 minus 4 over 0. Like I would have 0 over 0. And even though 0 over 0, you're like, oh, well, you can do that. You can't. You can never divide by 0, even if you're dividing 0 by 0. So we're going to have to take out that x equals negative 2 from our domain because that's the one spot that's going to cause issues for this problem.
So are your...
Go ahead.
I'm so sorry.
No.
I think I got a little lost. So
you're good.
The only reason that we're setting g of x to 0 is because it is in the original...
Bottom.
Okay.
Mm-hmm.
Okay. So even though it eliminates after we solve, we still have to
Yes.
keep that in mind. Okay.
Yes.
Okay.
Basically, when you're doing your division with your algebra functions, you're always going to take g of x set equal to 0 and figure out where those x's are. And then you want to take those out of the domain. Because even though they go away later on as we do the algebra, they cause issues. And we will see later on in the course, when it comes time to graph these are rational functions. And when we graph these later on, even though it's simplified out, what happens is in our graph, when we put these like on a Cartesian coordinate system, we have a hole at that spot. And so it's almost like it jumps over that. We will have a whole section, I don't remember what chapter it's in, but we'll have a whole section on rational functions where we talk more about like having these trouble spots that we have to eliminate out. So if we write it just with our set builder notation, we just write x such that x does not equal -2, because x can be literally anything else under the sun besides -2. -2 is the only issue. If we write it as an interval, then if we start with the smallest number x can be, which is -infinity, all the way up until we hit our trouble spot. We use the parenthesis because we don't want to include that trouble spot, and then we're going to union that from our trouble spot up through positive infinity. And we would do that for however many trouble spots we would have. I think the most complicated one you will encounter has like 2 trouble spots. So, good question though. Is there any other questions? Okay. Let's look at the difference quotient. And let's slide it up some more. So the difference quotient is really thinking about slope. That's really what it is. I'm going to zoom out a little bit because I want more of this to be on the wall over here. The difference quotient is using the average rate of change, which is the slope of nonlinear functions. We've talked about that. We talked about the average rate of change in the section where we talked about slope, because I told you the average rate of change is really how we find, quote unquote, the slope of a not straight line. And it's where we draw that tangent line in, that straight line, to connect 2 different points on our curved graph. And then we find the slope of that line, which gives us a pretty general idea of finding the slope of that curve, as you would. So the difference quotient is how we get closer and closer and closer to finding actually what the slope of that line is. If you continue on in math and you go into the calculuses, you will deal with the difference quotient and the average rate of change a lot, especially in Calc 1, as you start integrating and differentiating. Because what you're doing is you're finding how to maximize the space that's underneath so that you can actually get as close as possible to finding the slope as it would be of that curved line. Now, you don't need to know how to do calculus in order to do this in this class, because all we're going to do is we're going to do algebra. And what we're going to do is the difference quotient is this f of x plus h minus f of x all over h. Do you have to memorize that? No. Do you have to be able to plug in some values and figure this out? Yeah. And I'll show you with the example that we're going to do.
What is that word under the line?
Secant. S-E-C-A-N-T. Secant line. I think I said tangent line, but secant line. But this difference quotient, this f of x plus h minus f of x over h, what it is it's actually just the slope of that secant line. That's what this over here is showing you. Because slope is y2 minus y1 over x2 minus x1. Well, if we look at the picture that I drew here, where we start with this point x and then f of x, which is the y, and then we go over a certain amount that we're calling h, then we have x plus h, and then f of x plus h. So we're taking the y2, which is the f of x plus h, minus the y1, which is your f of x, all over your x2, which is the x plus h, minus your x1. And when we do that, the x's on the bottom go away, leaving us with this difference quotient. Again, you don't have to derive the difference quotient. You're not going to be expected to memorize the difference quotient. What you're going to be expected to do is what the problem is going to show you in just a second. As soon as you guys give me a thumbs up that you're ready to see the problem. Okay, I'm seeing thumbs up. I think I'm ready to move. Okay, moving. Don't look at the answers. Don't look at the answers. Don't cheat. I feel like you're cheating. Okay. Given f of x equals 2x minus 3, it wants us to find f of x plus h. Well, what do we do then? What do you think we do? Plug what in? So I think you're on the right track. What we're going to do is whatever is inside of here, inside of our function, this x plus h, we substitute that into the function in place of the x. So instead of 2x minus 3, we're going to have 2 times the x plus h minus 3. I substituted in the x plus h in place of the x. Then I'm able to distribute that 2 to the x and to the h and simplify it. They could give you a number in here like we had earlier, and we substituted it into the function in place of that x. They can give you an expression like this to where you substitute that in. And as we will see on the next section, they will actually have to where you can put a function in a function. And we'll do that in the next section. But that's all you're doing. So we didn't have to do anything else. We can't combine it any further. That's an x, that's an h, and that's a constant. So they're all independent of themselves. But they had you do that so that on this next step, you've already done some of the work. Because on the next step, it wants us to find the difference quotient. Well, the difference quotient is f of x plus h minus f of x all over h. So we're going to take that bit that we just found, this 2x plus h minus 3, that's this f of x plus h. Then we're going to minus the original function and stick all of that over h. The one thing to be careful about is with your difference quotient, again, that minus goes to everything that's in the original function. So when I first write it, I'm going to write that f of x inside of parentheses so that I remember to distribute that negative to everything inside. So then I'll have a minus 2x and a plus 3 because we have a minus minus all over h. So let's see if I can combine some stuff. I have a 2x and a minus 2x, so those go away. I have a minus 3 and a plus 3, so those go away, leaving me with 2h over h, which leaves me with 2. So my difference quotient between those two different points was 2. The slope between those two different points, or the secant through those two different points, was a slope of 2. Is there questions? I don't think there's another thing there on how I did that problem. Do you see how I didn't say you have to find the difference quotient? It asks you step by step to where you're doing different parts and using your algebra functions in order to actually come up with that information. In the notes, there is another one that I did. It's exactly the same way. Slightly more complicated, just simply because your f of x is slightly more complicated. It's a quadratic. And so when you start plugging in like x plus h into places with the x, you're going to have to square that first, which means you have to FOIL. And then you have to distribute the 2, and then you have to distribute the negative, and then you combine all the like terms. So the process is exactly the same. It's just a little bit more complicated algebra because you're dealing with a quadratic. And then when you do the difference of functions, or the difference quotient, excuse me, down here, luckily from step 1, you have that f of x plus h, so you would plug that in, and then minus the original. As you can see, the purpose of the difference of functions means that lots of stuff is going to cancel out, making it a lot nicer of an answer at the very end. You don't have to do that, but in reference, if you wanted another example, there is another example in the notes. Questions, comments, concerns?